Hey guys, welcome back to another study stream. In this study stream, we're going to be doing this problem. Most stones are moved with the same row or column. And yeah, all these problems are going to be about 2K rating and we're going to go up. So I think 2K is like reasonably difficult LeetCode hards, I'd probably say. And above what you'd get on interviews, but yeah, also good to practice on problems that are like harder than the things that you're actually going to get interviewed on, because then when you get the interviewed ones, it's going to be pretty easy for the most part. So yeah. And then also when you actually do get interviews and stuff, there's gonna be like pressure and all that stuff, so you're just gonna perform worse. So I like practicing harder stuff. Okay, so here we have a 2D plane. We place n stones at some integer coordinate. Each coordinate may have at most one stone. Okay, so basically we can't have overlapping stones. Stone can be removed if it shares either the same row or column with no stone. Given array stones, return the largest possible number of stones that can be removed. All right, so essentially I have this. Okay, so let's see. So they remove 5 stones. Okay, so you can't, so like if 2 stones are in the same coordinate, then you can remove one of them. So let's see. So 2 shares with 2 1. Okay, these share something, so you remove that. I guess 2 1 shares with this, or let's see, what does it share with this one? So you can remove the 2 1. 1 2 shares with this one, so you remove that 2. This one shares with this, so you remove that 2. This shares with this, so you remove that 2, and then you can never remove the last one. Okay. And there's 1,000. Okay. So that's a big hint, like constraints 1,000. That means we can have n squared, which is like kind of important. Okay, you can remove 3 stones here. So you, like here, you remove one of them. So let's say you remove that. This shares with this, so you remove that. This one doesn't share anything, so you have to keep that. And then this shares with this, so you have to remove this. So, okay. So I think I'm kind of getting it. So basically, we're looking for anytime 2 stones are in the same row or column, we can always remove one of them. And I think this is going to work well with union find. So I guess it's kind of hard to draw, so I'll do a quick little drawing to show what I mean. So let's say we have this grid, and we just have a bunch of like numbers. So 1 here, 1 here, 1 here. It doesn't really matter also the order that we do them in. Okay. So essentially, I think whenever you have a connection, you remove one of the stones. So like right now that you can't remove anything. So let's just pick like one stone and then we'll see if it shares with anything. So like we'll start with this one. Does it share with anything? And we'll circle it when it's done. So it doesn't share with anything, so we just skip it. Okay, how about this one? So this does share with this. So that means we can remove one of them. Doesn't matter which one, but we'll just say like one is removed. And this stone is done. Now here, this isn't shared with anything else, so there's just one. Now let's go to this one. It's shared with this, and there is a connection, so we can remove another one. Then this one, it's already shared with that, so we're done. This doesn't do anything. This doesn't do anything. So essentially, for every like connection, you can remove one of these things. So imagine you had like a bunch of these connected. Like this is connected to this, it's connected to this, and so on. So what that means is you can remove like there is always going to be an order in removing them, right? Because you can remove this because it shares with this, then you can remove this because it shares with this, then you can remove this because it shares with this, and so on. So essentially, we do a union find, and I think every time we have a successful union, we can remove the point. So I think that's the answer. And we can have n squared. So essentially we have like n stones. We just make a union find with n stones. And then we just, for every stone, try to union it with every other stone. And for every successful union, we add 1 to the result. So I'll kind of show you the quick demo for a union find. Pretty simple, to be honest. So you have a constructor. It takes in the number of points. In this case, it's n. And it has 2 items. It has ranks and roots. And so, and you can, like, I'm not going to do like a huge union find. I think I had a video on union find actually, but just do a brief overview. So for ranks, basically it's like the depth of the tree. So in the beginning, every node is its own root and every node is a 1 node tree. So that's just going to be basically we can just do arrays, or actually we can say ranks equals array, and in root same thing. And then we can initialize. So we can just say this. And basically the number of stones, we'll just label them from 0 to n-1. So ranks, so every stone will have a rank of 1 because every stone is essentially a tree by itself. And root, every stone is its own root. Root is like what's the top level root of the node. And in this case, everything has a tree of 1. All right, so we have 2 more functions. So we have a public int find. It takes in node. And if the ranks or roots of x does not equal x, so meaning like the node is not its own root, then we have to recursively get the root of that root's root, essentially. So we'll say roots x equals find on its recursive thing until we get to a node that's its own root, and then we kind of like recurse back, and essentially what ends up happening is that makes the tree height balanced. Or not height balanced, but it does a path compression, so find becomes amortized of 1. So then we do return roots of x here. And union, you can do some bunch of different ways. We'll just do a Boolean in this case. So what we really want to know is like, was a union successful? So pretty simple for a union. First, we get the top level parent. So x equals find of x, y equals find of y. And if they're the same, that means that these are already connected, so we just return false. And then if they're not the same, then we take the one with the smaller rank and we attach it to the one with the bigger rank, because that's going to make a shorter path. So if ranks x is less than ranks y, then roots x equals y. And we don't have to increase the rank here. And then the other case is x is bigger, or ranks y, I guess we do this way, is less than ranks x. Wait, whoops. That. Then we do the opposite, so roots y equals x. And if they're the same, you can pick an arbitrary root. So we'll just say roots y equals x. It doesn't really matter. And then whatever you pick as the root, you increase the ranks by 1, because that does increase the rank. And then we return a true saying it was successful because there's successful union. Okay, so we'll have a result. We'll have a nested for loop. First, we need to make the union find, actually. Find, and we need to do this. Okay, and then so we'll just do this. Essentially, what this does is we'll compare every node to all nodes bigger. That way we're not doing duplicates. We're never comparing the node to itself, so it'll still do all the comparisons. Looks like we got some error. Okay, so we need to check if they share a row or a column, because then we can do the union. So if stones I 0 does not equal stones j 1, or same thing, or 0, or same thing for 1. So 1. We'll just continue. And then we can just do this. We'll just call UF union find, or UF union on the indices. So if this is true, then we'll do 1. That. I think this works, right? Yeah. Okay, and then we just return the result, because essentially for every connection you're deleting 1. Right. I think this one. Ooh, I'm wrong. Why is that? This needs to be an and. Okay, still got wrong. Interesting. Let's so I think the easiest way to debug this is just going to be like print I just to make sure like we are actually doing stuff. And then see like, are we even hitting this at all? Right. So we are. So 0, 1, 0, 2. Okay. Union ij. So why is it saying it's false? Let's also print here, like successful union or something, just to make sure we are getting a successful union. Or not. Okay. So let's double check the union find real quick. Ranks. This is a mistake. Okay, how about now? Okay, there we go. I feel like it's a pretty simple problem for like a 2K. We'll see if we got it right, but I think we did. Okay, yeah. Okay, so then just like before, I like to read the tutorial, see if there's any other solutions. Depth first search, basically the same as union find, and I prefer union find, so I think that's fine. Not gonna do that one. And squared, same. Disjoint union is union find. Disjoint union set optimized. Component, union stones, offset, I don't know what. Is this O of n? Oh, interesting. O of n. Okay, so let's take a read how they got O of n. Union find, fill, count nodes, hash set, unique nodes, find. Okay, I'm not sure what they did, so let's just read a little bit. Differentiating, how do we distinguish union to address this? Okay. A stone is not the basic unit of the ground. Handle coordination range. Oh, so I see. So they're kind of cheating here, I'd say. I mean, it's okay. They're using like these values and storing them directly and then just like getting a count, which is okay, I guess. But yeah, I mean, you're basically taking advantage of the fact that this is like a small value, which is pretty reasonable. So yeah, I guess you can do this in linear, but I'm pretty happy with this one as well. Let's see if there's anything else. No. Optimal solution. Can't say. Yeah, interesting. And I would say, yeah, I'd recommend learning Union Find. It's one of the rare graph ones that like it just makes it a lot easier than DFS or anything for problems that call for it. Like you can kind of see how here, like it makes total sense and the code's really easy. For DFS, it'd be a little bit more. And honestly, Union Find's not that hard. You can learn it, code it pretty quickly. So yeah, I don't think so. Generally, I like the GPT to optimize, but here there's like nothing. Like you can't really make Union Find better than this unless you use that other one, the linear. And there's nothing to improve. So if my code looks a little messy, then I'll put it into GPT to see if I can make it better. But in this case, I don't think there's anything. Okay, and then yeah, just write like the time and space and all that. So this is n squared and space. So the Union Find is n, and that's it. Okay, yeah, definitely one of the easier ones. I'd say out of this rating problems, I'm probably not gonna be able to do like 20% or something like that. See how it goes, and yeah, I'll kind of show my thought process if I get stuck, and like how I unblock myself and figure it out. But yeah, it's gonna be all for this one. Hopefully you liked it. If you did, please like the video and subscribe to the channel, and I'll keep making more of these in the future just to do. Yeah, I think it'll get really interesting once we do like harder problems with harder algorithms like segment trees, binary index trees. I can explain a bunch of stuff there. But yeah, thanks for watching.